Welcome back to the course on audio signal processing for music applications. In the previous two theory lectures, we presented the sinusoidal model, the analysis part. Now, in this third and final lecture, we will finish the topic by talking about the synthesis part of the model, therefore by generating a sound out of the analysis that we did. We will first review the model and the concept of spectral peaks and spectral tracks, and then we will focus on the concept of sinusoidal synthesis, what is also called additive synthesis. And then we will finish by talking about the complete system, the complete sinusoidal model system that does analysis and synthesis. So as we showed in the last lecture, the sinusoidal model considers that the sound is the sum of time-varying sinusoids, and it's expressed by this equation in which the output signal is the sum of sinusoids, of time-varying sinusoids. So a good way to show the results of the analysis is to plot the frequencies of the time-varying sinusoids on top of the magnitude spectrogram of the sound. Of course, each sinusoid, apart from the frequency, it has also magnitudes and phases which are not shown. So for example, in this plot, here we are showing the spectrogram of a flute sound that we can listen to. And then on top of that, we are showing these lines, which are the frequency tracks of the sinusoids that have been identified. Of course, again, there is much more than that, but it's a quite good compromise, and it gives us quite an intuitive visualization of this sinusoidal model. But now, from these values, the ones we have analyzed, we want to synthesize a sound. The standard way to synthesize sinusoids is to use additive synthesis, and this is the standard block diagram of an additive synthesizer, in which we have a series of oscillators, each one from an input of a given amplitude and frequency. It generates a sinusoid, a time-varying sinusoid, and then we can sum all these things together to generate the output. But how do we generate each individual sine wave? The most straightforward way to generate the sinusoid is to use the sinusoidal function directly. So this function that we see here can be easily implemented in a programming language like Python, like you see here. So we can have specific amplitude frequencies to control this function. But this is quite expensive, especially when we deal with complex signals in which we might have to call these functions hundreds of times and at every sample. So let's propose another way. We can use the DFT to do synthesis. So if we start from the spectrum of a sinusoid and do the inverse Fourier transform. So in this equation, we show how to do it. So basically, we start from the magnitude spectrum of the sinusoid and the phase spectrum of the sinusoid, and we just take the inverse DFT of that. So here, the plots show a very special case in which we would have the spectrum of a sinusoid that has one of the discrete frequencies of the DFT or of the FFT. So we just have one value, and then we just take the inverse DFT of the whole array, and we get this nice looking sinusoid of length 64. Too bad that things are not that simple. This only works for these frequencies that have a very discrete frequency, one of the DFT ones. But we know also how to represent sinusoids that might have frequencies different from these discrete frequencies. So such a sinusoid does not have a single spectral value. It has values for all frequencies, values that depend on the window that we consider. And then to generate a sinusoid in the frequency domain, we have to generate the transform of a window and place it at the right frequency, amplitude, and phase. So in here, this equation expresses this idea that the magnitude spectrum of the sinusoid is in fact the magnitude spectrum of the window shifted to the right frequency and multiplied by the right amplitude. And again, the phase spectrum is also the phase spectrum shifted to that particular location. And the plots show two examples of two different windows. So the same sinusoid with a different window applied to it, of course, is expressed with different magnitude and phase spectra. And then when we take the inverse of that, we get a nice looking sinusoids, of course, with the window applied to them. But in the time domain, all samples have the same weight. And one great advantage of the frequency domain is that not all samples have the same weight. So we might take advantage of that in order to make this whole process a little bit more efficient. For example, this emphasizes the idea of the main lobe of these windows. Those samples, the samples of the main lobes, are the ones that carry the most weight, the most amplitude. So in the examples before with the Hamming and the Blackman-Harris, we can now plot just the spectrum of the main lobe samples. And here we see the main lobe samples with a dark red and the rest of the samples with a light red. And then if we just take the inverse DFT of just those samples, of the samples of the main lobe, well, we get these blue shapes, these sinusoids, which from a first look, they look okay, but if we actually measure the signals to noise ratio, so basically how this would be distinguished from a real sinusoid, a very synthetic sinusoid that would be perfect, we see that the Hamming window has a bigger signal to noise ratio than the Blackman-Harris window, because of course the samples of the main lobe of a Hamming window carry less weight than for the case of the Blackman-Harris. So in the Hamming window, the signal to noise ratio is 63 dB, and in the case of the Blackman-Harris, it's very good, it's 102 decibels. So basically the distortion or the noise is insignificant for audio applications. So it's clear that the Blackman-Harris is a good choice for generating sinusoids in the frequency domain. We just need 8 samples, which are the main lobe of Blackman-Harris has 8 samples. And if we just take those 8 samples and do the inverse, we can generate a sine wave as long as the FFT we have. And then if we want to generate several sinusoids in the spectrum, we can just generate several main lobes. So from this equation, we can see that the sum of sinusoids in the frequency domain is the sum of main lobes, the sum of the main lobes of these windows, in this case of the Blackman-Harris windows, because as we will see is the one that we'll be choosing. So in this example, we are generating 3 sine waves, one at 1000 Hertz, another at 4000 Hertz, and another at 8000 Hertz. So we place the main lobes of the windows in those locations, each one with a different amplitude. We also generate the phases for those main lobes, and we can just take then the inverse DFT of this spectrum, of this combined spectrum, and we get a signal which is in fact the sum of these 3 sine waves, of course multiplied by a Blackman-Harris window. Okay, and then we can put together an analysis synthesis approach using this idea. So we start from a sound, a fragment of a sound, in this case an oboe sound. Then we compute the spectrum, we find the locations, and this we can use any window, any DFT size, any FFT size, so it's whatever is appropriate for the analysis. And then we basically do an additive synthesis approach in the frequency domain by generating main lobes from these cross values, from these peak locations. The FFT can be a different size. The window in this case is a different one because we're using a Blackman-Harris window. And then we do the inverse of that. And hopefully this resynthesized sound is identical to or similar to the original one, of course, with now the idea that we have a Blackman-Harris window applied to that. But we have one problem, and that's the problem of overlap in the process of synthesizing. The Blackman-Harris window requires a big overlap. If we want to generate a time-varying signal, the overlap of a Blackman-Harris should be very high, even bigger than 1/8 of the window length. So the solution is to undo the Blackman-Harris window and apply a window whose overlap factor is a little bit better. And this is a proposed approach that is commonly used, which is, as we see in the top plot, is our synthesized signal, which has this Blackman-Harris window applied to that. And then what we're going to do is divide by the Blackman-Harris and multiply by a triangular function. But we're going to do it on not the whole size, but only on half of the size. So in fact, what we're going to do is multiply by this third shape. So we will divide by the Blackman-Harris and multiply by the triangulars, or multiply by this third shape that we see here. And then the result is a similar function than the previous one, but now this function, which is half as long, has been multiplied by a triangular function that can be overlapped by 50%. So that's pretty good. So like would be 25% of the initial size. Okay, so this is our approach that we will be doing, and in which we can do an overlap of 25%. That's the one we required with this process. So we start with the spectrum, with the Blackman-Harris windows. Then we do the inverse with the Blackman-Harris, and then undo it and apply the triangular function. And that's it. We're done. We can do analysis, synthesis using sinusoidal approach. Like we did with the STFT, we can put it all together into an analysis synthesis system. So we start from x of n, our signal, our complete signal. Then we multiply by our analysis window, compute the FFT, obtain the magnitude and phase spectrum, and now we are starting with the sinusoidal analysis. We're starting with the detection of the peaks, detecting in the magnitude spectrum, the location and the amplitude and the phase of the peaks, and then we can track those peaks in time by applying some of these constraints of continuity of the frequency values, so that we construct sinusoidal tracks. So we have a track per every time-varying sinusoid. And this is our analysis results. We have these tracks of sinusoidal values, and then we can synthesize with what we just explained in this lecture. So we can do it in the spectral domain by generating these main lobes of Blackman-Harris windows, which is quite efficient. We just need to generate 8 or 9 samples per sinusoid in the frequency domain, and then compute the inverse Fourier transform and obtain the synthesized sound, which we can undo the window of the Blackman-Harris, apply the triangular function in a way that we have an overlap at process that works at 25%, and it reproduces quite well the original sound in some way, or at least a part of it. Let's see an example. So this is an example of an analysis synthesis using the sinusoidal model. So this is a sound of a bendir, which is this Turkish drum. It's one stroke of it. Let's hear that. Okay, and then the analysis shows just the tracks, the sinusoidal tracks that we have obtained. So we see only the frequencies of them plotted in the time frequency space, and then from those we can synthesize the sinusoids and hopefully recover the sound. And let's hear that. If you pay a little bit of attention, well, it's not exactly the same. Especially in the attack, you can hear some difference, and that's one of the things that we will be trying to work on in the next few lectures. So for the references in these topics, as I said, there is not much. For additive synthesis, there is quite a bit, but you can look yourself in Wikipedia, and again in Julius' online book you can find some relevant material. And this is all for the sinusoidal topic, at least from a theoretical point of view. We will also demonstrate and do a more programming approach to that. In these 3 lectures, we have started from the short time Fourier transform, and we have seen how to analyze sinusoids on top of that. And this is a way to simplify the spectrum. So in fact, it can be used for compression, but at the same time is a very useful representation for many other things, as we will see in future classes. So we'll continue in this direction towards a more useful and higher level representations that capture some of the prominent essence of a given sound. So next class we will take advantage of some of the characteristics of the sound to apply some more constraint in the model, so that hopefully we'll get some other aspects of this analysis, synthesis, that can be of interest for many applications. So thank you for your attention, and I see you next class.